challenge is trying to decide like whether or not you even need to use u-substitution. You saw there were some problems where you needed it, some where you don't, and that's not always going to be disclosed up front. And on the AP test, they're not going to say, "Oh, you need to use u-substitution on this one." So I'll continue to kind of mix them together. We have some that are and some that not, so that way you really kind of get a better feel for when to use this technique. But sometimes you can use the technique when you might not expect to use it. And you saw a problem on your quiz that was the integral of tangent x, which at first when you look at it, it doesn't really look like it's going to be a u-substitution problem. But then when you start thinking about the derivative rules that you know, this is not a derivative where you know what its antiderivative is, at least not up front. And so what you can do is do some clever manipulations to force it into a situation where you can use the u-substitution strategy. So like, and it looked like at least most of y'all got this right. I didn't look through every paper. But we can, if we rewrite tangent as sine over cosine, then we can use u-substitution to find this integral. Okay, if we let u be cosine x, then du would be negative sine x, and although I don't have negative sine x in the expression, I can manipulate that just like if there was any other constant in front of there, and divide both sides by -1 and get negative du is sine x dx. So then once I rewrite it like that, I can make my u-substitutions pretty easily and just work it like any other u-substitution problem. So this integral would be, since cosine is u, it would be like 1 over u, or u to the -1, times negative du, but I'm going to bring that negative out to the front. And just so you know, and you've probably noticed this as we've gone along, I really haven't made a point to like call it out, but anytime you've got a coefficient in front of whatever expression you have here inside an integral, you can always factor that outside of the integral, like move that negative sign outside, or if you have a coefficient of 2, you can move that outside the integral. Just for future reference, know that you could do that, and I might take advantage of that later on today, but like in other words, you could write this as like negative integral of u -1 du. You don't have to do that. It really doesn't matter. You're going to end up in the same place. But just know that that is something you can do. Now we know that the integral of u to the -1, or 1 over u, is the natural log of the absolute value of u. So this would be the negative natural log of the absolute value of u plus c. And since u is cosine x, we get this lovely formula for the integral of tangent x. Now, there's always like, or how should I say this? Trigonometric functions can be easily manipulated because they're all sort of related to each other, right? And you can actually do some manipulations to this to write this integral a little differently. Now, this is good. Like if you can come up with this, I'm totally happy. You're going to be great on the AP test. But you should know that sometimes, like if you look this integral up online, you might see that some websites have this listed as natural log of the absolute value of secant x. And I don't think it's at least immediately obvious how you would even get there, right? Like, how is this equal to natural log of secant x? You see it? Okay, how you can get there is logarithms have some special properties, one of which is if you've got a coefficient in front of a log, you can rewrite that as an exponent of the argument. And so you could rewrite this as natural log of absolute value of cosine of x to the -1. And the reciprocal of cosine is secant. So I don't want you to get confused if you're like looking stuff up online. You're like, wait a minute, I thought it was negative natural log of absolute value of cosine. What's going on with the secant stuff? This is how you make that transition. And so both of these are correct. They're just two different expressions that represent the same thing. Okay. You can use a similar u substitution to work out the integral of cotangent. All right, here, I can rewrite cotangent as cosine x over sine x. Okay, let me put all that red, actually. And instead of using cosine as our u, here we're going to want to use sine. So say let u be sine x, where du would be cosine x dx. Now here we have that cosine dx directly, so we don't have to manipulate the du equation at all. We can then rewrite this as the integral of u to the negative 1 du. Okay, we know that integral, 1 over u, is natural log of the absolute value. So we get the natural log of the absolute value of u plus c, which is the natural log of the absolute value of sine x plus c. Now, while you might need to know these integrals for the AP test, I wouldn't bother memorizing these. I mean, these are kind of hard to memorize. There's like a lot going on here. I think you're probably better off just knowing that, hey, if I ever see integral of tangent or cotangent, I should just use u substitution and just solve it right on the spot. I think you'll be more likely to get it right than trying to memorize negative natural log of the absolute value of cosine x. I mean, we've got like a triple composite function there. Yeah.
Why do you use absolute value instead of just regular parentheses?
Because so this is something we talked about back when we originally went over this one, is that the domain of 1 over x is all real numbers except for 0, but the domain of natural log is only positive values. So you run into an issue where like the original function 1 over x can take in negative values, but the integral can't, right? So to ensure that all of the inputs going into that natural log function are in the domain, we force all the negative inputs to be positive. Yeah. So it's really just like a little quirk of the domain restrictions there. Okay. Now the real focus for today is going to be on how to use u substitution on definite integrals, which are these integrals where we're trying to essentially find the area under the curve. Okay, and there's not really anything too fancy or novel about what we're about to do here. There's just one little thing you have to look out for. And that is when you make your u substitution. So like here, this is from an old AP test. It says using the substitution, they even tell you what the u should be. So that's kind of nice. They say, all right, well, u is 2x plus 1. So what's du? Yeah, 2 dx. Now, in this particular problem, you don't have that 2 in there, right? So this is not a perfect match. We need to divide both sides by 2. We get 1/2 du equals dx. So that's all good and fine. And I mean, you could integrate this. You know, I could have put this on your quiz, and you would have been fine, except for the fact that there's upper and lower bounds here. So the only thing you really have to look out for, we can rewrite this with the u's. Let's go ahead and do that. So the integral. Well, let's actually not do that yet. So when we make those substitutions, when we switch over from x to u's, when we switch over from the x's to the u's, we need to also switch the boundary values. Because what these boundaries represent are like vertical lines on your graph. Like if, square root graph looks like, something like this, and we want the area from like x equals 0 to x equals 2, right? That's kind of the idea here, right? And so these boundaries, those vertical lines, represent x values. They are the x values that are partitioning the area that you're interested in. But when we switch over to u's, we are essentially modifying where the boundary should be. And so what we need to do is convert these x values to u values. Now the conversion is going to come from your u substitution. The relationship between x and u is given in the statement that you make initially. In this particular problem it's given, but u is 2x plus 1. So when you switch over from the x's to the u's, you need to adjust these boundaries accordingly. So to find the new upper bound in terms of u, we got to say, okay, well, that's going to be 2 times 2 plus 1. I'm substituting that into this equation here, right, to find, okay, given any x value, what should the corresponding u value be? Right, yes. So the same thing with the bottom boundary. We want to convert that to a u. So when we go to set up this new integral in terms of u's, now the upper bound is 5 and the lower bound is 1. We've got 1/2 square root of u du. And like I was saying earlier, anytime you've got that coefficient out front, you can always factor that out of the sum. So 1/2 integral from 1 to 5 of root u du. So this is something that's easy to miss, but also easy to get right. Okay, just you have to kind of be ready to look out for that. The key takeaway from today, if you only walk away today with adding one thing to your calculus knowledge, let it be that when you convert from x's to u's, and it's a definite integral, you also convert the boundaries. All right, let's take a look at number 2. We've got the integral from 0 to 2, x squared times 1 minus x cubed cubed. So what do we want u to be here?
1 minus x cubed.
1 minus x cubed. What do we want du to be? Or not what do we want it to be, but what is it, I should say?
It's negative 3x squared.
Yeah, du is negative 3x squared dx. We do want to rewrite that because we don't have negative 3x squared, we just have x squared. So we need to divide both sides by negative 3. And then before we start making substitutions, we also need to go and convert the boundaries. So 2, if u is 1 minus x cubed, this is going to be 1 minus 2 cubed. And the lower bound would be 1 minus 0 cubed.
Negative 7, 0, or 1, sorry.
So yeah, the new boundaries going to be 1 minus 8 is negative 7. And on the bottom, we've got 1 minus 0 is just 1. And this would be negative 1/3 u cubed du. Now, I would recommend at this point and just sort of moving forward, factoring out that coefficient every time. So I'm going to actually rewrite this as negative 1/3 times u cubed du.
Do we need to flip the integral for this one?
You don't need to, you can. The only difference would be if you did, then this would become positive. But you don't have to. The fundamental theorem is going to take care of that. So you're always going to do, like, as we're about to do, use that fundamental theorem to evaluate this. We'll find the antiderivatives, and then just plug in negative 7 as the first one, and 1 is the second one. Even though they're backwards, that's okay. Okay, so this is going to be negative 1/3 times the antiderivatives of u cubed So that would be, what would that be? 1/4, u to the 4th. Okay, of course, plus c, although we know there's going to cancel out, from 1 to -7. Now, just to make this a little easier, I'm also going to factor out this 1/4. Just take that out too. So I have -1/12 from 1 to -7. Just really kind of trying to simplify this as much as possible. And yeah, again, we know the plus c's are going to cancel out. So the fundamental theorem says we're going to substitute in -7 and then 1, and then subtract those. So we're going to end up with a c minus c. Yeah.
Remember, just like us, you did.
So let's go ahead and plug in those values. So we have -1/12 times -7 to the 4th minus 1 to the 4th. Now, I'm not going to make you do -7 to the 4th by hand, so we're just going to leave that as our answer.
It's a big number.
Yeah, it's going to be pretty big. Any questions about number 2?
So we would never plug back in like the 100. It just stays.
You don't have to. Yeah, isn't that nice? Yeah, you don't have to go back and substitute. And the reason why you don't have to is because we're changing the boundaries.
I see.
If we didn't change the boundaries, then we would have to go back and replace it. And you don't want to do that.
Yeah, I'll just give the same thing.
Yeah. Advanced placement.
All right, let's try the next one. Here we want u to be 2x minus 1. So du would be 2dx, although we have 1 dx. So I'm going to divide both sides by 2. I also need to convert the boundaries. So 5 is going to become 2 times 5 minus 1. 1 becomes 2 times 1 minus 1. So the new upper bound is 9, and the new lower bound is 1. So now let's convert everything to u's here. We've got the integral from 1 to 9 of u to the -1/2 du. And then, actually, we have an extra 1/2 on there, don't we? So let's write that out in the front. All right, so now we can integrate or find the antiderivatives. So there's going to be 1/2 times, increasing that by 1 brings it to 1/2. Dividing by 1/2 is 2. And we're going to go from 1 to 9. 2 times 1/2. That's going to simplify to 1. So we can make this even easier and say, all right, well, this is just going to be u to the 1/2. That's really just square root of u from 1 to 9. And this one I think we can actually get away with working out. I think this one's reasonable to expect you to come up with an actual answer and simplify it. Because we've got the square root of 9 minus the square root of 1. That's 3 minus 1 is 2. Any questions so far?
Would we lose points if we didn't completely work it out?
On a free response, no, that's okay. But I would imagine this would probably be like on a multiple choice or something where they would expect you to do that. But yeah, if you want to leave it, if it's just like, if you want to just get in the habit, on especially free response, of just stopping here, that's okay. I'm fine with that. This one just happens to be really easy. Yeah. there's not going to be like a hard line where I'm like, oh, if it's this complicated, then don't simplify. And if it's like, it's hard to like make that line of like when you should simplify and when you shouldn't. So just don't. On the free response, you don't have to ever simplify a numerical value. As long as it's logically equivalent, you'll get full credit. All right, number 4. Yeah. Oh, yeah, let's back up. So when we find the antiderivative, we need to increase the exponent by 1, bringing it to 1/2, and then you divide by whatever that new exponent is. So dividing by 1/2 is equivalent to multiplying by 2. All right, number 4. Here, our u will be x squared plus 1. My du then would be 2x dx. Although you can see pretty clearly, like, we don't want a 2x dx, we just want x dx. So we're going to write this as 1/2 du equals x dx. And before we start making any substitutions, let's find our new boundaries. So 3 squared plus 1, that'd be 9 plus 1 is 10. 1 squared plus 1 is 2. So we have the integral from 2 to 10. There we go. Of, what would this be? 1/2 u to the negative 1 du. And we know the integral of u to the negative 1. We've done that several times today already. And it's just the natural log of the absolute value of u. Okay, so this is going to equal 1/2 times the natural log of the absolute value of u from 2 to 10. Which would be 1/2 times the natural log of 10 minus the natural log of 2. You don't really need those absolute value bars anymore because you could just straight up evaluate it, right? Like the absolute value of 10 is 10. The absolute value of 2 is 2. Now, this problem actually came from a multiple choice question, and the correct answer choice was 1/2 natural log of 5. Okay, this is using a logarithm property that says when you subtract 2 logs with the same base, you can combine them by dividing the arguments. So this is going to equal 1/2 times the natural log of 10 over 2, which is natural log of 5. So sometimes those logarithm properties are going to come up. Just be ready for those. Number 5 says, what's the average value on the interval? This takes us back to the last unit, right? Average value of a function, which is where we find the definite integral on that interval and divide it by the length of the interval. So this would be the integral from 0 to 2 of x squared root x cubed plus 1 all over 2 minus 0. So we need to integrate that numerator. That's where we're going to do the u-substitution. We're dividing by 2, so it might be nicer to write if we write this as like maybe 1/2 times the integral. But let's work through that integral first. We're going to let x cubed plus 1 be u. Then du is 3x squared dx. We want to get rid of the 3, so we're going to divide both sides by 3. And we do need to change the boundaries. So 2 cubed plus 1. 2 cubed is 8 plus 1 is 9. 0 cubed is 0 plus 1 is 1. So now I'm going to rewrite this. And this is like we're dividing by 2 minus 0, dividing by 2. But I'm going to rewrite it as like 1/2 times just to clean it up a little bit. Still dividing by 2. Of the times the integral from 1 to 9. So yeah, what do we have here? We got 1/3 times u to the 1/2 du. And actually, I think I'm going to take that 1/3 out, factor that out like we did on the previous problems. 1/2 times 1/3 is 1/6. Yeah. Okay, so now let's find the antiderivatives. So that would be u to the 3/2 times 2/3. And then technically there's a plus c there, but we don't really care too much about that. So we know it's going to cancel out. We can also take out that 2/3. 1/6 times 2/3 would be 2/18, which is 1/9. So we've got 1/9 times 9 to the 3/2 minus 1 to the 3/2. And you could probably simplify that pretty easily, but I'm just going to leave it like that. Right? The square root of 9 is 3. 3 cubed is 27. Square root of 1 is 1. 1 cubed is 1. So you could work this out pretty easily. You could do it in either order. You'll get the same thing. It's just usually easier to take the square root first, right? Like, because cubing 3 is probably going to be easier than cubing 9 if you don't have a calculator. Yeah. Okay, but you can leave it unsimplified. That's totally fine. All right, one last problem here. It says let g be a continuous function using the substitution u equals 3x minus 1, which means that du is 3 dx. The integral from 2 to 3 of g of 3x minus 1 dx is equal to which of the following? Now, g is just a generic function. We don't know what it is. But looking back at that du, it says 3 dx, but we don't have a 3. We just basically have a 1 dx. So we need to divide both sides by 3 to actually use this. Now, this is the type of question that we already saw one that was kind of like this. Like, this is probably what you're going to see on the AP test as far as like u-substitution of a definite integral goes, where really the only tricky part is remembering that you do have to change the boundaries. Everything else will go sort of according to plan, but these boundaries, if you forget to change them, you're going to get it wrong. So if u is 3x minus 1, and that upper boundary will be 3 times 3, which is 9 minus 1 becomes 8. And the lower boundary, 2 times 3 is 6 minus 1 is 5. So this will be the integral from 5 to 8 of 1/3 gu du. So look at our answer choices. It looks like it's D. Any questions about u-substitution?